Yes, thanks. So hello, everyone. I'm Gabriel Laffitte, and with me is Alix de Cremoux, also machine learning engineer. And we both work in the artificial unit at the Bank de France. So today at Nodes AI, we wanted to share with you a very concrete use case. Over the past few years, we have been using LLMs and more broadly NLP techniques to automate tasks at the bank. And one of our most common use cases is turning unstructured documents into structured data. So taking a 400 pages PDF and extract clean and usable information from it. But extraction alone isn't enough. We need to know whether the data is correct. We need real-time quality, evaluation, explainability, and outputs that domain experts can use straight away. In this talk, we'll show you how we address these challenges using LLM for extractions, Neo4j for validation and structuring, and a chatbot on top for analysts. Let's get started. Here is our agenda, 4 parts. So why a central bank needs a knowledge graph for corporate structures? Second, how we extract entities and relationships for PDF reports using LLMs. And third, how do we duplicate and match against the official registries? And fourth, Alix will take over for the conventional agents. So let's go into the business context. Let me set the scene. Here is the landscape we are dealing with as a central bank. On the left, we have structured data coming from multiple sources, national registry, private registry, aggregators, international datasets. So each of them is responsible of its own data quality. These sources can be linked together, and when you connect them, you get a solid baseline, standardized, machine-readable, and accessible via APIs. On the right, you have unstructured data, things like PDFs, newspapers, and online publications. So it's literally text, images, plus a timestamp. So the challenge now is to build a data processing layer that brings everything together. So let's take a concrete example, glyph data. It's a unique identifier, for instance, an ID used to identify entities involved in the financial transactions. But glyph doesn't cover everything. Not every entity has an LAI, and not every relationship is reported. So we ask ourselves 2 key questions. First, how reliable is the data? Can we measure its quality and trust it as a baseline? And second, can we enrich it? Can we connect it with other sources to fill in the gaps and build a more complete pictures? This is where unstructured data become very valuable. Take annual reports. For example, there are long public documents where company describe their structures, subsidiaries, partnerships, and joint ventures. This information exists nowhere else. And if we can extract that information and turn it into structured data, then integrate it with glyph, we can start comparing, we can start validating, and we can start enriching the data sets. And that's exactly what we have built. So how does we go about this? On screen, you can see the full pipeline. We'll come back to several steps in details on the next slides, but let's leave the full pipeline. Think of it as 2 tracks. The top tracks is our reference baseline. Glyph publish a golden copy 3 times a day, every 8 hours. Each time we pull the delta, so what changed, and we reshape the data into nodes and relationships. And then we'll load it into Neo4j. It's a classic ETL, extract, transform, and load process, but the target is a graph, not a table. So it's lightweight, it's incremental, it's fully automatic. And the bottom track is easily lifting. That's a batch process. We identify the entities we need to investigate it. We go find their annual reports. This is published online, and we feed them into the document taken. So then the NLP pipelines kick in. we chunk the PDFs by chapter, structure way, not sliding window. So each chunk carries determinist metadata, chapter name, page, range, position. That's where we had the real value. So because none of that is stochastic. Then the LLM extractions, entities, and relationships are structured JSON chunk by chunk. Once we have both track, the fresh baseline and the batch extractions, everything in stage 4 converges in Neo4j. This is where Neo4j native graph powers really matters. So we deduplicate, we match, we match extracted entities against the baseline, and we compare structures not to nodes, relationship to relationships. And it's on all the volumes, millions of entities, thousands of comparisons, it's all depths. And by the end of the process, we have built a validated, enriched knowledge graph. From there, in stage 5, you can really start unlocking value through a semantic layer, which Alix will talk about in a few minutes. Let's go into the NLP enrichment. So the first step in the pipelines is chunking. And honestly, this is where we learned the most. So when we started, we did the naive thing, fed the old document to the model, one shot, 400 pages in, and we got about like 15 entities back. Just the big name for chapter headings, everything, the footnote, the appendices, the substrate lists, gone. The model wasn't bad. Maybe the prompt was bad, but we were just giving it too much. So literally, we switched to structured chunking. So these are digital PDFs. They have a table of content. So we can read it. We split by chapters, corporate overview, group structure, partnerships, risk factors, financial statements. Each one becomes its own chunks with its full context window. Same prompt, same model. We went from 15 to 150 entities, 10 times more just for smarter chunking. But there is another benefit people don't always think about. Once you have clean, independent chunks, you unlock a lot of on your infrastructure sites. Each chunk is a self-contained request. So you can parallelize massively, you can batch, you can scale. And you don't need the biggest model for every chunk. Some chapters are simple. Some are complex. You can route accordingly. For this demo, we used Gemini 2.5 Pro, but in production, having small independent chunks mean that you could use a lighter model. So maybe on-premise. That matter for cost, for digital sovereignty, and for not throwing your entire infrastructure at tasks that don't need. And for private, confidential data, you have to use on-premise LLMs. And the last one is traceability. Each chunk carries deterministic metadata, chapter names, page range, position. That doesn't come from the LLMs. It's come from the PDF structures. So when we extract something, we always know exactly where it came from. And in a supervision context, if you can't explain the provenance, the data is useless. On screen, you can see what it looks like in Neo4j. Each node is a chunk linked to the next. On the right, the property field, the properties, file, name, position, length, text contents. That's our foundation. So, okay, now we have our chunks, but what do we actually tell the model? We didn't just write a prompt and hope for the best. Well, at least we did it the first time, but we optimize it. This approach is inspired by a method called automatic prompt optimizations. It is from a paper from Pritsant published in 2023. The core idea is simple. Think it of a gradient descent, but on text. You take a prompt, you run it on few labeled examples, so paragraph when you know already the answer, and you look what the model got wrong. And then you rewrite the prompt to fix those mistakes. Did it meet links? Did it meet noise property? Did it miss some data? You make the instruction clearer, so, or you just add an example that covers that case, and then you run it again. If it's improved, you keep the change. If it overfits, you roll back and you repeat. The beauty of fits is that you don't need a huge data training, a huge training set. You need like 10 to 20 annotated paragraphs to do so, not thousands. And this whole thing is modular. The graph schema, the entity types, the relations types, it's a parameter. So you can, so actually, we used like 7 entity types and 7 entity relationship types aligned with Glyph. But if tomorrow we need to process ECG reports, for example, we swap the schema, we label a few examples, and it adapts. On screen, you can see left one chunk, one extraction, and on right, the full graph. It is an example of an entire report. So let's go into the entity resolution. So at this point, next slide. At this point, we have two things in Neo4j. The Glyph data. It is the data we need to check, and the LLM extraction coming from the annual reports that have been verified and that now we can trust. The question is simple. Does what we extracted actually match Glyph data? First thing we do is deduplication and create connection between extracted structures and Glyph. We are making a bridge to see like if same company, different names across chapters, and we need to find if we need to find the entities in the Glyph baseline. So we merge on normalized data plus jurisdictions. So that takes us from 150 extractions down to 80 distinct entities. So now the interesting part. So we are comparing the extracted structures against the Glyph data. So, but we don't just check the entity by entity process. We compare at 5 different levels. So let me walk you through the key ones. First, entity overlaps. Are the company present? Are the company the same in both graphs? So we use Jacquard similarity. And if you find like 3 common entity out of 5, that is like 60 of the groups confirmed. Good start. Second, the structure. So this is where it gets topological. We are not just asking, are the same node here? We are asking, is the shape the same? So the control chain, the depth, the hierarchical. So we use graph edit distance for this. A score of 1 means 1 leaks is different. The structures are almost identical. Third, centrality. Is the same entity at the top. If entity A is holding company in both graph, great. But if it's a different entity, that's information we need. Something needs to be, we need a closer look. But we also compare links and attributes also, but you get the idea. So 5 levels from the big pictures down to the details. And the key points, all of these run in Neo4j. Centrality, algorithms, graph comparisons. No need to export in anything to like a relation base or. And at the end, we are creating extracted node with all the information about these comparisons to have enriched nodes, and that we can push into the semantic layer. All right, that covers extractions, validations, and a graph. That's my part done. Now the real questions. You have this beautiful knowledge graph, but how do people actually use it? That's where it gets really cool. So Alix is going to show you how we put a chatbot on top of this.
Thanks, Gabriel. So we now have two complementary layers, a trusted corporate graph providing authoritative relationships on a side and a noisy but valuable enrichment layer from another side, which data extracted from documents. The key question now is how do users reason over both? This is where we move from graph construction to graph consumption through an agent. Before the architecture, let's see what this enables in practice with a small demo. We start with a question asking for a company and its subsidiaries as we were a business analyst. I think it's in pause. Sorry for the delay. So at this point, the agent kicks in. It routes the request to the right domain-specific path. Because in fact, we have multiple sub-agents that can query either the graph database, but also other databases that are based on classical database, for classical RAG. Before we go... Okay, thanks, Amir, from the chat. So before we go further, there is a key step, human-in-the-loop validation, because in real data, multiple entities can match the same name, and we do not want the system to decide for the user. We want the system to ask the user to clarify its mind and to confirm whether the found entity is the right one. While the system is reasoning, it is producing a lot of outputs that could be auditable by the user. For example, the user is able to see all the steps taken by the agent, also how the human in the loop was taken into account, and also, of course, the retrieved data from the graph. So this can be visualized in multiple ways. The user is able to see the Cypher query, but also the retrieved data as a tab, but also as a graph, of course. Now let's move to a second question. So we are going to take a subsidiary found from the parent and ask for its enriched data. This time, the system goes differently and think in a different way. It goes beyond structure. It retrieves document-derived signals. So the chatbot responds with all extracted information from related financial documents. But importantly, we still keep the graph RAG context. So every piece of extracted information is grounded in the graph structure. We also kept the visualization layer, so the user can still see the graph traversal and the retrieved entities. We are currently adding one more layer on top of it, a document-level visualizer. So users can open the exact chunk where the signal came from and see it directly inside the document for editability purpose. So what we are building here is not just a chatbot. It's a system that connects questions, graph reasoning, document evidence, and visual traceability. Classical RAG works well for local facts, but it breaks when questions become multi-step, and in finance, they almost always are. The issue is simple. RAG retrieves text, but it does not understand structure, or it does poorly, very poorly. GraphRag changes that in the way that it moves from retrieving text to navigating relationships. Let's take a concrete example. Which subsidiaries show risk signals? To answer this question, we need to go through a reasoning path. First, by identifying the parent, then traversing ownership, and following by collecting subsidiaries, and finally, aggregate signals. And this need to combine deterministic structure, the graph, and probabilistic signals with NLP. And importantly here, we are not reconstructing the structure from text. We trust Glyph for the structure and use NLP only for enrichment purposes. Even with GraphRag, queries remain complex and ambiguous. So we introduce an agent, not as a chatbot, but as a reasoning system. The agent takes a question, breaks it into steps, decide which tool to use. Graph traversal, semantic search, it chooses. So most of the time it's both, and it needs to be combined in a meaningful way. Then it combines all the tools' outputs into a structured answer. Important, the agent doesn't know anything. It only coordinates the tool. Other tools, some tools can be very simple and generic, but some really depends on the business domain, sorry. About explainability, which in finance is highly critical. We need traceable step, explicit tool usage, and reproducible reasoning. We also add human-in-the-loop validation, so users can validate entity and also correct enrich relationships if they are false or partially incorrect, and also refine signals. So this is not a black box. It's an entirely controllable system that is going to improve through time. And this controllable system is based on a unified data layer, that is Neo4j. In fact, we use Neo4j for three purposes. First, to build our domain graph, which is based on corporate structure. Secondly, as a vector layer, to search into documents and evidence. And thirdly, as an agent memory layer, to store the history and the reasoning steps. It's important to distinguish two databases. In fact, we separate domain graph and vector from the agent memory layer because the business graph is really authoritative when the agent memory is dynamic. This improves traceability, debugging, and control. And also, it allows us to deeply manage permissions as we deeply not want our agent to introduce new nodes or change the structured data that we should trust and not modify at all. There are some well-known tools like LangChain that allow us to quickly build that kind of agent and workflow. And it also allows us to have one unified stack instead of multiple systems that allow us to go quicker to production. So let's go to our end-to-end architecture from a consuming side. At the center, you can see the conversational agent that orchestrates everything, and it relies mostly on two capabilities. On the left, the graph database capabilities of Neo4j, which is mostly for query structured data, and on the right, the vector retrieval capacities of Neo4j. The key idea here is that the two capabilities are highly connected. As Gabriel explained, we linked the entity within the structured data to the document which they appears in. So the agent don't have to choose between text and structure. It combines both and level each of them separately and together. The agent uses this to build reasoning steps and produce explainable answers. We also kept memory for traceability and human validation for control. So in the end, we move from fragmented systems to a unified reasoning platform. To conclude, we move from fragmented financial data sources to a unified reasoning system. We combine multiple trusted structured data, document understanding, and agent-based reasoning. The key idea here is simple. We are not replacing structure with AI. We are augmenting the structure with AI. In order to add traceability, human validation, and a unified platform like Neo4j. This becomes deployable in a real financial context with high needs on security, for example. So ultimately, I would like to emphasize that it's not only a chatbot, it's a highly reasoning system. Thank you very much. We're happy to take your question now. And if you have time, we'd really appreciate your feedback that the QR code on the right.
So I saw in chat different questions that all are already being responded by Articus. So do you have other questions?
Yes, regarding maybe I can take the one. Regarding the visualization, as Atticus answered, we are using Neo4j NPL. It appears to be the simplest tool to do so. And also there are a lot of tutorials online.
For the chunks methods, you are absolutely right. Like we went from this method because we handled financials reports, and those financial reports are following a strict method. Like there is a table of content on it, so it's why we decided to pass this. But there is a fallback, there a callback into a chunking method, really based on the number of tokens your model can handle.
So there are also some questions in the Q&A section. We did not have a GitHub now. As we are in an institution and have very high constraints on security, we cannot share this for now.
Okay, how did you get the domain user feedback on the fine-tuning of prompts? But we are working at the Banque de France, so we have user feedbacks for the prompts. And I can see
about the chat interface, it's custom built. For now, we are not ready to deploy this interface in production. It's only for testing purposes. And we have a dedicated team that is working on building interface compliant to the EU AI Act.
And thanks. I think we are done for this session.
If you have any further question, feel free to connect either through our mails or LinkedIn.